We're working on the page 113 questions on the heat equation here. This is a theory question. You just have to kind of read it. So it says, okay, you've got a rod of length 10, you've got the heat equation, there's some stuff about initial conditions and boundary conditions. But the question just says, find what happens as time goes to infinity. What happens to the temperature? And this is kind of just a remark. As time goes to infinity, the temperature goes to the steady state temperature. And in steady state, now all this is just a remark. We'll write down the solution maybe in black. In steady state, what it means is you're not changing in time. So to be steady state would say that the temperature is not changing in time, so the rate of change of temperature with respect to time is 0. And if you look at the heat equation, that means that the second derivative of steady state with respect to distance is 0, and the curves that have a second derivative of 0 are straight lines. So maybe even I'll just write down y is equal to, we're talking about y equal to mx plus c. Okay, so this is enough for us to go and write down. We know that it's going from 20 to 100. So write down our actual solution here. So it's going from 20 to 100, and there was a rod of span 10. It's going from 20 to 100. And this is temperature versus distance. And so it's going from here to here in a straight line. And when you've got the graph in front of you, it's very, very easy to write down stuff like rise over run and where it cuts the y-axis. So it's going from 100 or 20 up to 100, so the rise is 80, and the run is 10 because it's going from x equals 0 to x equal to 10. So the slope therefore is 80 divided by 10, which is 8, and then we can write down our answer. So I won't write down y because the y coordinate is temperature, so we're talking T is equal to mx 8x plus c is where it cuts plus 20, and that's that first question. That's all it's looking for. Okay, another very short question here. So again, there's a setup about the heat equation, initial conditions, boundary conditions, blah 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 blah. And then when it's using the explicit method, which we'll see later in this video, what is the condition on lambda to ensure convergence and stability? Now, I might just ask this slightly differently, so I'll just make a remark. So for stability, need this lambda to be less than a half. What happens if lambda is bigger than a half? No matter how small delta t and delta x are, your approximations go to infinity when they should be going to a steady state, to a straight line. Now the other thing, convergence. Now, what we're gonna say, instead of asking about convergence, we're gonna say for good transient. And this also is required for this. So the issue is that if your lambda is between a half and a quarter, bigger than a quarter, the approximations will go to the steady state, but the only good approximations you'll have is your initial values and your steady state. In between, it's not going to necessarily be very accurate. But even if your delta x and delta t are very, very small, but if your lambda is less than or equal to a quarter, you're going to go towards the steady state, and your approximations in the middle are going to be very good. And if they also take delta x and delta t going to 0, your approximations are going to the errors are going to 0. So the answer is going to be you're not going to be asked about convergence explicitly, you're going to be asked for good transient. So what is the condition on lambda to ensure stability and good transient? So it means that the approximations between the initial and when you stop, when you're close to the stopping condition, are going to be good. So the answer to this is as simple as lambda less than or equal to a quarter. That's all I'll be looking for there. Okay, do note with this question that the work solution is on page 170. So if you're able to kind of, you have this video as well as that. Okay, well, anyway, off we go. So we'll do part A here. So we've got again transient state temperature satisfies the heat equation. We have a rod here of length 4, and we must chop it into 4 pieces and chop it and label appropriately. So let's draw the rod here, and it goes from x equal to 0 all the way over to x equal to 4, and chop it into 4 pieces like so. So this is x equal to 1, x equal to 2, x equal to 3. And we can space there. And the temperatures. Now the temperature on the left should be fixed, and here we see temperature 0, 0 is 100. That actually should be for all times, but yeah, they're fixed forever. So 100 on the left and 60 on the right. And we just have to come up for names for the temperatures here. So we'll call this temperature 1, it'll change in time. This one temperature 2, it'll change in time. And this one temperature 3, it'll change in time. And that's us good for A. For each of the 3 internal nodes, so there's 3 of them there, carefully use finite differences to write 2.16 in this form. So we've seen this in lectures. We'll go through it here. So we'll just, you can have a look at, maybe we'll pause here and try and find the formulas that you'll be given in your written exam. Okay, so these are the finite differences here on the right that you'll be given. So the middle one is for calculating the heat flux density vector, and the others are what we're talking about. Now, you want to be able to kind of read these, so can I write this? So this is kind of next, the I plus 1 signifying you're at the next x point, and this is the current. And then this is the next, for approximating the second derivative. This is the current, and then the xi minus 1 means at the previous x point. So we'll be kind of using these. Now the actual partial differential equation is up here. It's 0.21. So we've got 0.2 second partial derivative of temperature with respect to distance is equal to the partial derivative of temperature with respect to time. Now what we're going to do is we're going to kind of set up like this rod here changes in time, but all of the points, temperature 1, temperature 2, temperature 3 at any point can be put into the following kind of schematic. So these are 3 different points. So like if this is temperature 1, it's 100 temperature 1, temperature 2. And when I say this, I mean this one here. This could be temperature 1 or temperature 2 or temperature 3. This Ti minus 1 is the temperature to the left, and this Ti plus 1 is the temperature to the right, but that's in the x-axis. What about in the time axis? Well, the time axis, we're going to go in this direction, and it's the same distance, so it's I, but it's at the next time. So these are all at the same time. These are L's, and this is at the next time, L plus 1. So in terms of the formulas over here, this is next with respect to time. For both of them, this is the current. This one over here is the next with respect to distance. And this is the previous with respect to distance. Okay, and now we're going to use those finite differences on the right to approximate the things in the partial differential equation. So approximating now this, we have 0.2, and now let's approximate the second derivative there. So it should be the next temperature, and this is a partial derivative with respect to x, so these are next with respect to x. So the next one over with respect to x is Ti plus 1L minus twice the current, which is TIL, plus the previous Ti minus 1L, and divided by delta x squared. Now I'm going to put in delta x, but in a second we actually know what delta x is. Maybe we'll just remark on that now. If we just go up for a second, the delta x is the distance between the temperatures. The delta x is actually equal to 1. Now this is equal to, now we're using kind of the we're using the time axis. So we're approximating the partial derivative with respect to time. So up in the top right here, the next temperature in terms of time is TIL plus 1 minus the current TIL divided by delta T. And delta T for us at the moment, we can't really, it's just delta T is delta T. Okay, so our job is to solve this. So what's it asking us to do? Find TIL plus 1, so the temperature, a certain temperature at the next time in terms of the previous. So our job is to solve for this, and we'll do that carefully. Just a small remark, remember in a partial derivative, here the time is constant, and here the x is constant. So here you'll see that the time doesn't change, and for this one you'll see that the distance doesn't change. Okay, so now let's solve this for the thing on the right. A is equal to b implies b equal to a, and that means I'm going to write these the other way around. What I am going to do here is I'm going to multiply both sides by delta t. The right, which will be the left, multiplying by delta t gets rid of the division by delta t. Let's check I'm recording properly. It's been a while. So this is multiplying the right hand side by delta t, gets rid of division by t. And now on the left hand side I have 0.2 times delta t, and I'm going to pull out that delta x squared. And then what have I got in here? I have the previous Ti plus 1 minus twice the current Ti. Well, I say previous in time. I should say current maybe. Okay, and now to solve for what we want, we just have to add the TIL. We end up with something that looks a little bit like Euler's equation. The next Ti is equal to the previous, or the current Ti, plus some kind of step size thing, which is what we call lambda. So this yoke we call lambda, and we want that to be less than a quarter, or equal. Okay, that's that. I think that's us done on that question. Have we written? Yeah, we've carefully used finite differences to write the heat equation 2.16 in that form. Okay, find the transient state temperatures at the 3 internal nodes at time twice delta t. So we know what's going on at 0. So this thing here tells us that at time equal to 0, the internal temperatures are all 0, and we want to find out what's happening 2 time steps later, so we need to use this formula twice. Now, just in case you kind of missed what's going on, we'll just make a little remark at the start of this that says that, what does the notation mean? TIL is our approximation to the temperature. Now the I means that it's I delta x's, and the L means that it's L delta t's. So that's what we're doing here. Okay, and so for us we need to go and go from the initial temperatures, which are all 0, which we might actually write down just as a part of the remark. So let's just write down the initial scenario. So T0, 0, well, that's the temperature on the left, that's always 100. Temperature 1, 0, so that's one of the internal points. The question says that starts at 0, as does temperature 2, as does temperature 3, and temperature 4 starts and remains at 60. Now we should also calculate the lambda here, and I might somewhat unfortunately I have forgotten my calculator, so I'll have to use something else. Hopefully it'll be okay. Okay, so if we put this into the calculator, delta t is 0.1, that's in the question, and delta x is 1 squared, that's the distance between the temperatures. That lambda is equal to 0.02. Okay, and now we're going to use the equation that we derived, this one, to approximate temperature 1, temperature 2, temperature 3 the next time, and also the time after that. And I think it's important to use the notation. And now if you get the answers there, I'm happy enough, but I think you kind of show understanding if you use the correct notation. So temperature 1 at time 1. So it's the previous temperature 1, which was 0, plus lambda. I'm just going to write lambda. Now this here, I don't know how much of this is showing up. That doesn't quite show up, unfortunately. Anyway, so in here I have the next temperature over minus twice the current temperature plus the previous temperature over, all at this previous time, which in fact is the initial time here. So the next temperature over is the previous T2, which is 0, minus twice the previous temperature 1, which is 0, plus the next temperature over, so you're talking temperature 2, temperature 1, and 100. Using calculator, this is equal to 2, I believe. So actually I'm copying this from the worked example at the back, so hopefully there's no mistakes in that. Temperature 2, the next temperature 2, so the previous temperature 2 is 0 plus lambda, and now it's the next temperature over, this should be 0, the next temperature over the current previous. So the next temperature over is 0 minus twice the current plus the previous, and this of course will just be 0. And then temperature 3, 1 is the previous temperature 3 is 0. And now what are we doing? We're going to do, I need to put in T3 equal to 0 there again. I'm going to use the next one over is temperature 4, then temperature 3, then temperature 2. Okay, so the next temperature over is temperature 4. The previous temperature 4 was 60, minus twice the current, which is 0, plus the previous. And this is coming out at 1.2. So this is what's going on at time. This is our approximations at time equal to 0.1. And the question is asking for 0.2, so we go again. So we're talking temperature 1 at the next time is the previous temperature 1, which is 2, plus lambda. And hopefully we can understand what's happening now. So it's the next one over, which is the previous T2, which is 0, minus twice the current, which is 2, plus the previous, which is 100. On the calculator here, cheating, I get 3.92. Temperature 2 is the previous temperature, which is 0 plus lambda. And now we're talking, temperature 2 is kind of surrounded by temperature 3 and temperature 1 and itself. So the previous temperature 3 was 1.2 minus twice the current temperature 2, or should I say the previous temperature 2, well no, current 0, plus the previous temperature 1, which is 2, and out pops 0.064, and temperature 3, 2, previous temperature 3 is 1.2 plus lambda, next temperature over is 60, minus twice the previous temperature 3, which is 1.2, and then the previous temperature 2, which was 0. And we get out 2.352. And that is our answer. Question D is about what happens when time goes to infinity. Well, we've seen a similar question already like this, so we'll just do it really quickly. And we won't kind of explain it. So we know it's going from 100 down to 60. So the slope here is going to be negative. The distance, I think, is 4. Yeah. And so we get a slope of the rise. Now, because it's going down, the rise is negative, minus 40. Over the run is 4. That's minus 10. So you're talking temperature is equal to mx minus x plus c is where it cuts 100. Okay, so it's in steady state. When time goes to infinity, it's just a straight line between the temperatures that you know. What we got up here? Last question. Hence, suppose that the calculations in part C were to be continued. So if we were to continue these calculations here, when should we stop? Well, what we can do here is we can calculate using the formula or otherwise if what happens, like what's temperature 1 infinity if time went on forever. Well, you can look into this 1, 2, 3. Now that's 1, 2, 3 because they're the distances, and sub those x equal to 1, 2, 3 into the steady state and get that this is 90. Sub x equal to 2 into the steady state and you get that this is 80, and you get that this is 70. Now your approximations, because the lambda were less than or equal to a quarter, will get closer and closer to this. So what you should do, the stopping rule is until the absolute value temperature 1 minus 90, so that's the distance between temperature 1 and the steady state, is less than 0.5, and the distance between temperature 2 and 90, sorry, not 90, 80 is less than 0.5. And like you could be tempted to do a stricter one, but you'll find actually that once it's within 0.5, it really takes it quite a long time. I guess it might, yeah, I mean, if you like, yeah, okay. And then have we any more questions there? No, we don't. I guess this is very similar to the previous, but we'll just carry it through quickly enough. Might make more sense, try it yourself. So this is a 2-meter long rod. Okay. So x equal to 0 here and 2, and it's asking to cut it into 4. So in terms of x's, it's a bit different to last time. The delta x here being 0.5, and so this is temperature 0 is the left hand side, so that's x equal to 0 is 50, and over here it's fixed at 10, and again this would be temperature 1, temperature 2, temperature 3. That's us mesh the rods and label them appropriately. Then using delta t equal to 0.01, you're just repeating this calculation that we did up here. The only difference, I guess, is like this number is actually the same again. So it's just the delta t is small. Oh, and the delta x as well. So we might just write down the lambda here. So the lambda in this question is k, which is 0.2 times delta t, which have to be given in the question, and the delta x you get from your picture is the distance between them is 0.5, and that's to be squared, and you get 0.008. Okay, so that is essentially, I'm not going to do out B again, but the formula is temperature that I could be 1, 2, or 3. L plus 1 means next time is previous temperature I in time, or we could say current. Well, previous works because we don't have current and previous are kind of synonymous here, plus lambda, which is 0.008. And then it is at the previous time here, 3 temperatures. The next one over in distance minus twice the current plus the other next one over. So the first I plus 1 means, T3, say, and I minus 1 there would mean T1, but obviously it depends. So are they all starting at x equals 0 yet? That's given there. So they all start at 0. So we'll quickly do these calculations. So we've got the next T1, the next T2, and the next T3, and these are all at time 0.01. That's the time step here. So we'll kind of do them maybe all at once here. Maybe it helps. So the previous temperature 1 is 0, previous temperature 2 is 0, previous temperature 3 is 0. All of them plus lambda, they're all the same. So I'm just going to write lambda as that 0.008. And then, so the formula there means the next one over. The next one over from temperature 1 is temperature 2, and the previous temperature 2 is 0. The next one over from temperature 2 is temperature 3, and that previous one was 0. And the next temperature over from temperature 3 is that 10. Minus twice the current distance. So this would be temperature 1, and the previous temperature 1, well, that was 0. The previous temperature 2, well, that was 0. And the previous temperature 3, well, that was 0. Plus the next one over. So this is, I guess, the one to the left. So left of temperature 1 is the 50. Left of temperature 2 is temperature 1, the previous value was 0. Left of temperature 3 is temperature 2, the previous value is 0. So this is giving me 0.4, 0, 0.08. Okay, and now the next time, so we're talking temperature 1 at the second time, temperature 2 at the second time, temperature 3 at the second time. So we're talking, in each case, the previous temperature 1 was 0.4, previous temperature 2 was 0, previous temperature 3.08. Plus lambda, that 0.08. It's a weird way of writing it, but hopefully they're just changing it up. And then this one means the temperature to the right, the previous temperature to the right. To the right of temperature 1 is temperature 2, the previous value is 0. To the right of temperature 2 is temperature 3, previous value 0.08. To the right of temperature 3 is that 10. Minus twice. Now the TIL is where you were. It's the same as the first numbers there. So that's times 0.4 minus 2 times 0 minus 2 times 0.08. And then plus the temperature to the left. To left of temperature 1 was 50. To the left of temperature 2 was temperature 1, and the previous temperature 1 was 0.4. And to the left of temperature 3 was temperature 2, and the previous temperature 2 was 0. So hopefully you can kind of see what's going on there. This is coming out as 0.7936. This one coming out as 0.00384. Remember, it's a very small time step. And then 0.15872. And that is a wrap on the heat equation.